Right, hello everyone, I'm Nicky Bloor, and as Dom said, here to talk about practical serialization attacks. I'm a managing security consultant at NCC Group. I've been there for about 5.5 years now. An ex-software developer, written all kinds of software from desktop applications to web stuff to games, ICS stuff. I think of myself as a hacker. I like to solve problems. I like to break stuff, build stuff. I like to build stuff to break stuff. Outside of work and technology and all this kind of stuff, I'm a hiker and rock climber. I might not look it, but I am. And I am next to DB on the internet, so Twitter and so on. So, start off, hands up if you would know what to do with that packet. If you saw that packet during an application assessment, would you know what to do with it? Cool. So, start with a quick story. I went to a customer site to do a web application assessment. And when I rocked up on site, they said, you need this version of Java. I was like, that's a bit strange for a web application assessment, okay. So I figured it might be a Java thick client application that communicates over HTTP. So I got a VM, built correct version of Java on there, and while I was waiting for login credentials from the customer, I started playing around with the application, submitted some false credentials, having a look what happened. I saw a bit of traffic flowing through Burp Suite, but everything didn't seem to be going through there, so a couple of login attempts, and the application responded and said something like account locked out or whatever. I was like, that was a bit strange, so fired up Wireshark and sent some more of these login requests to see what was happening. And each login attempt that I submitted ended with a packet similar to the one that I just showed you, traversing the network. So it was actually a Java application served by a HTTP page. Nothing else had anything to do with a web application assessment. So that packet that I just showed you was a dummy login packet. So I submitted just random credentials in the application. And that actually led to the discovery of a vulnerability that had survived multiple previous pen tests. But it allowed me to access a server that, for the most part, looked pretty well secured on the outside, but on the inside was, the server and the whole environment was weak, insecure. From that server, I managed to jump around the entire supporting infrastructure. I think I had access to some 20 or 30 servers, multiple data centers. I jumped between the pre-prod and the prod environments, had the Unix admins running around going crazy, going, what are you doing? I think my slides are buggered up a bit there, but I would have missed that vulnerability as well. I survived multiple previous pen tests. I would have missed that vulnerability as well. But I've had quite a bit of exposure to Java serialization because I've done bits of research over the last few years. So as soon as I saw that packet, I recognized it straight away, and I knew exactly what I was going to do. And I set out putting together some scripts and attacking that application. And so in about half an hour, I think it took altogether, I'd rooted the first server. From there, I could basically jump around the whole network. I can actually read raw serialization hex bytes because I've looked at it that many times, manually decoding it and debugging. So obviously that packet that I showed you contains serialized Java data. And the goal of this talk today is to help improve your understanding of Java deserialization vulnerabilities, lower the bar to attacking these vulnerabilities, and sort of help you to recognize potentially vulnerable targets and then use existing tools to enumerate and attack these targets. First thing that I should probably say about this is that practical doesn't mean point and click. Generally, attacks against serialization are more involved than other common vulnerability classes, but with the right tools and knowledge, the complexity should be similar to a bit of manual SQL injection. So you've got to put a bit of work in to exploit the target, but the rewards are quite significant. So we can often get remote command execution using serialization attacks. So it's obviously important to understand how serialization works in order to attack it. So we'll start off with a bit of key background information. Briefly, serialization is the process of converting runtime program data, variables, objects into a format that can be stored or transmitted. So into a byte stream or various different formats. The reverse process, deserialization, converts records that are stored on disk or in a database or network packets back into in-memory variables and objects. The more complex the data structures are, so if we're using a language that supports object-oriented programming, the more complex the serialization process needs to be able to turn arbitrary data structures into a byte stream and back. And the more complex the serialization process is, the more scope there is for, vulnerabilities, things to go wrong. There's no fixed format for serialized data. You can serialize data into simple text formats such as JSON and XML, binary format, or you can use a lot of high-level languages have a built-in format and built-in serialization functionality. For this talk, we're going to focus on Java's built-in serialization. Just keep things simple. But the high-level concepts, same kind of ideas, do apply to other technologies such as PHP. So in Java, built-in serialization is dead easy to use. If you create a class in your Java program and you want that class to be serializable, simply implement the interface java.io.serializable. You don't have to do anything more. You can then pass that object to object output stream.write object, and it will serialize it into a byte stream, whether that's going to a file, over the network, whatever. And then to get that object back, to deserialize it, you call object input stream.read object, and you can get those bytes, convert them back into a runtime object. The actual data format can be described as a simple stream format. It starts off with a 2-byte magic number, hex ACED, should be at the start of any serialization stream. That's followed by a 2-byte version number. I've only seen version 5. There might be older versions, in future there might be newer versions. And then following that, there is at least one content element. The first byte of a content element tells us the type of the content element, and from the type we can infer the structure of the data that follows in the stream. There can be more content elements, and you can continue reading depending on how you're reading that serialized data. Java might keep reading that data until it hits the end of the stream, and then that's return the result. And there are various types of content elements. So, for example, null, which is nothing. So, if you have a class description and it's not got a superclass, then you might see a null content element for the superclass. Object, array, so on. And like I said, that first byte tells us the format of the data that follows. The serialization protocol can be found, the specification of the format can be found online on the Oracle website, but it's a bit unclear in places. So I've got some examples to show you what serialized Java data can look like. First one is a minimal stream. So we've got the ACED, so the serialization header, 0005, which is the version number, and then 70, which is null. The string AA. This time, byte 5 is 74, which is a string content element. The next 2 bytes are the length of the string, so 4, and then the string bytes themselves. And now we've got a simple object. The object has no properties, so the data in that stream, 73 is an object, 72 is a class description. We've got the length of the class name itself, serial version UID, and then some other things like class description flags and superclass. So in Java, we deserialize objects using the java.io.objectsinputStream class. The data that's passed to this class is passed sequentially, so reads each byte one by one. Data is instantiated instantly, so if there is an object element in the stream, as soon as Java gets to the end of that object's data, it will instantiate that object in memory. And there's little to no validation done. So validation is essentially handled by exceptions. So if, for example, we want to read a string object from a stream, we can do objectInputStream.readObject, cast that to a string, and then assign that to our string variable. If the object returned by readObject cannot be cast to a string, an exception will be thrown there. A class cast exception. So that's where validation happens, but at this point, readObject has already read the bytes from the stream, instantiated that object in memory, and then that's the point where generally our payload is already executed. If we make a class serializable by implementing the serializable interface, we can provide a readObject method, and that can be used in place of Java's default readObject, or it can be used alongside it. So you can, for example, use your own readObject method to implement backwards compatibility with different versions of the same data for different versions of your application. But we can use that essentially to handle the object loaded event. So given class implements serializable, we have a readObject method, and we can handle the event that an object of that type is loaded into memory. An example use of that might be, we might have a class that manages database connectivity and interaction with a database. We could serialize it to save the database connection settings and then deserialize it. And at that point, we might use readObjects to establish a connection to the database automatically. So, deserialization vulnerabilities occur when we as an attacker control the data as being deserialized. That allows us to control the properties of the objects being deserialized, or even the type of the objects being deserialized or instantiated. By controlling that data, we can potentially control the flow of code that uses that data. So if there's an if statement that is based on a property of an object that's deserialized, we can control the outcome of that if statement, which branch it takes. So we can control code that is within the serializable.readObject method that we implement on a class, and we can control code potentially that interacts with a loaded object. So if a program calls objectInputStream.readObject, uses that return value in some way, we can potentially control that code there. So, exploitation of deserialization vulnerabilities is known as how we exploit it by controlling properties of objects and using that to manipulate the flow of execution of code is called property-oriented programming. Our payload consists of objects, properties of objects that control existing code, and that's something that seems to trip people up with deserialization vulnerabilities. We're not providing code to the target to execute, we're providing properties that manipulate the code that already exists. So the code that we control is known as a POP gadget, a property-oriented programming gadget. It's just a snippet of code that we can control through the properties of an object. You can think of it like a high-level rock gadget, but instead of just pushing a value to a stack, we might have a POP gadget that writes data we control to a file. We might not control a file name, so generally, same with rock gadgets, we need multiple to create a full-blown exploit. So we might need another gadget that's going to rename a file or move a file. Exploitation relies on knowledge of the source code. If we don't know what source code's there, we don't know how we can manipulate it. So how do we attack serialization vulnerabilities without source code? There's a tool, Serial. If you know anything about Java deserialization vulnerabilities and attacking them, then you'll have heard of it. So there are lots of third-party libraries that are out there. If you're developing a big application, you don't want to be reinventing the wheel, so use existing libraries that do whatever you need to do. But those libraries are obviously contain code, and we know what that code is. So Serial has a load of POP gadget chains that work for common libraries. And it's an amazing tool for attacking serialization vulnerabilities. Most of the payloads, not all of them, but most of them lead to blind command execution. And we're going to focus on those payloads for this talk. So, with background information covered off, let's have a look at how we attack serialization. First thing, we need two main things, but we're going to talk about three to attack serialization. First thing we need is an entry point. We need to know where we can provide data to the application so that the application will deserialize it and execute a payload. We need POP gadgets, POP gadget chains that the application is aware of so that we can manipulate those to do something advantageous. And because we're looking at blind command execution, we need appropriate commands to execute on the target. So the entry point could be any part of the application that deserializes data. If we have access to source code, then we can look for things like object input stream.read object. We can look for serializable classes in the read object methods and look at what code is in those methods or around that code. If we're looking at the application from a black box perspective, then we can look for the serialization header. So the byte is ACED0005, followed by a byte in the range hex 70 to 7E. So here we've got an example of some data that's obviously binary data in Burp Suite. Switch over to the hex view and we can see ACED000573. Again, Wireshark, TCP packet, ACED000573. Text-based protocols and formats such as HTTP and XML could also wrap serialized data, but they're more likely to basic store encode the data because it's a binary format. But that also generates a recognizable pattern. So we're looking at basic store encoded data. We see lowercase r, uppercase O, 0, uppercase ABX. That's the serialization header. So there are other hints and indicators that we can use to identify Java serialization. If we look at suspected serialized data in a text or ASCII view, then there are various strings that should stand out. The first and most obvious are Java class names, java.lang.object, com.foo.a, and so on. They might also be in an alternative format, and that's the serialization protocol, and that's part of the specification where they use. Sometimes you need this format. Begins with a capital L and ends with a semicolon, and instead of dots between the namespace parts and the class name, we've got forward slashes. And we've also got the strings SR and XP. They appear just, again, as a side effect of the serialization format. So SR commonly appears, that means we've got essentially an object content element followed by a class description content element. So you'll see this bytes 7372, which is SR. XP, similar. So a class description can have annotations, and they must end with a end block data content element, which is the X. And then if the class has no superclass, we'll have a null content element, so that's a P. So we go back to that login packet. We can see those indicators. So we've got string SR, java.lang.short, java.lang.number, and we've got XP. But there's one thing missing in this packet. We don't have the serialization header. So the first byte of the packet there, 79, that's a reset content element. So in a serialization stream, certain content elements are assigned a handle. So if we have a string, for example, in a content in a serialization stream, that string might be repeated throughout the stream and in other parts of the stream for whatever reason. There's no reason, and it's easier to assign that string a handle, and then later on, if you need to use that string, you have a reference to that original instance. So the first handle that gets assigned to an element that has a handle has a specific value, 7E0000, and then each one has that incremented by 1. The reset element resets that counter, that handle value, back to the default. So it's basically, it's like saying start a new stream here. That's followed by 7.3, which is an object, 7.2, which is a class description. But the important point is you might not see the serialization header. And the story that I started off with, that client had an IDS in place which looked for serialization attacks, missed everything that I did because it was looking for this in the same packet as it was looking for the payload objects. So we've identified an application that's using serialization, and so the next thing that we need to do is work out where we can inject our payload into that stream. So the simple case is we have the serialization header followed by a byte in the range hex 70 to 76 or hex 7b to 7e. Those two ranges are the content types that Java can read when you call object input stream.read objects. So they're things like null can be returned, reference, a string, an object, a class description. All these things fall in those ranges. And if you call object input stream.read object, and any of those exists in the stream at that point, at the current offset, they'll be read as an object. What that means is we can inject an arbitrary object into a stream at that location, and that will be read as an object. So we can infer, kind of reverse infer that that offset will be read as an object. So a common alternative at the start of the stream, instead of one of the bytes listed there, we might have a block data or a block data long element. So we'll have the serialization header, followed by one of the two, either hex 77, and then a single byte that represents the length of the block of data, and then that many bytes of data. Similarly, 7A for block data long, which has a 4-byte length field, followed by that many bytes of data. If that is then followed by a byte in one of these ranges, we can inject a payload at the offset of that byte. So here we can see an example with a block data element at the start. So we've got 77, 08, we've got the bytes, 1122, so on. And then that's followed by a 73, which is an object. So we can inject a payload at that offset. But what about more complex cases? We basically, this is why I said I can read hex raw serialized data, because I've spent loads of time having to decode things and debug things. I've done it that many times that I wrote a tool that will do it for me now. So what we can do with serialization dumper, I'm releasing this, I've got the link at the end of the slides. I've released it, sorry. We can pass the raw hex bytes of a serialization stream to serialization dumper.jar, and it will pass it in accordance with the serialization format and specification. It doesn't pass everything at the minute. It passes everything that I've needed to pass it to decode, which should do for most cases. But you can see there, it's dumped out. We've got a TC string element, TC null, TC reference. All of those offsets in that stream can be replaced with an arbitrary object, our payload, and provided the application that reads this data calls read objects to read those, then we can execute a payload. One thing to note there is you can take the hex values that were dumped out by serialization dumper and rebuild the stream from them, except you need to ignore the new handle lines, because that's the handle value that was assigned to that string. So we can see that string with handle value 7E0000, and then a reference that references that string, except I've put FE00. That should be 7E at the bottom. So what we can do with that is we can pass that, a chunk of serialized data we've seen passed around by some application, decode it, work out if there is a content element of, so things like TC string, where the byte that tells us the type of the content element is in the range 70 to 76 or 7B to 7E. And we can replace that element in the stream, send that at the target, and it should attempt to deserialize it as an object. So we've got an entry point. We worked out how to identify entry points. We need to find some pop gadgets that we can use. To find gadgets, like I said before, we need to access the source code. We can review read object methods, code around read objects, and work out what that code does with the data that's read from the stream. But it's not very practical doing that, and we might not always have the source code. So yeah, we're gonna use essentially YSOL serial. We're going to target common libraries. So the first thing that we need to do is work out what libraries are there. What libraries can we attack? Because there are a lot of YSOL serial has payloads for maybe, I don't know, 15 or 20 libraries, or 15 or 20 different payloads. We need to work out which libraries the application uses. So ideally, we'll use background knowledge or an information disclosure issue to identify libraries that we can use. And then if that fails, we can kitchen sink it. We can throw everything but the kitchen sink at it. So if we know what libraries are available to the target application, we know what gadget chains we can use. So this is a partial mapping of jar file names of libraries to YSO serial pop gadget chains. So commons collections -4.0.jar, we can attack that with the YSO serial payload commons collections 4 and so on. There are some overlaps in YSO serial payloads. So for example, there's a commons bean utils payload that relies on an outdated commons collections library in order to attack in order to exploit that, or generate to get command execution. So we might as well just use the commons collections payload in that case. So kitchen sinking. This is a snippet of Python that I've used a few times in attacking these kind of vulnerabilities. Essentially, just got a list of YSO serial command execution gadget chains. We call YSO serial with a given command, payload command, generate the bytes, and then we pass those on to a function fire payload, which is implemented in whatever way needed to deliver that payload to the target. First thing that I should say about that is that kitchen sink approach is potentially risky. There's always a risk of triggering an unhandled exception in the target application, which might crash the target. In practice, it's unlikely that we're going to do that because even an nmap version scan would crash the target if it can't handle this malformed data. I've never come across anything that unstable. But if we scan a box and we knock that service over, you're probably going to knock it over again if you try this kind of attack against it. It goes without saying that throwing all possible payload types at a target is noisy. It's going to lead to more log entries being generated, obviously a lot more network traffic than just attacking a specific library. And then the other issue is that these command execution payloads are blind. We don't get any command output back when we execute one of these payloads. So how do we know that those pop gadgets and chains are available to the application, which ones are available? If we're throwing all possible payloads at it, at the application, the target. How do we know that the actual command we're trying to execute is available? So ideally we need some feedback from the target. So one option, and common option, is to try and ping our own machine, monitor network traffic to verify whether the payload command executed. Remember to limit the ping count if you do that. Have the server pinging and pinging and pinging, and because I buggered my script up the first time round, I did it again, and the server was going nuts pinging me. And then there was 10 or so processes that were just constantly pinging my box. So a better option is actually send an invalid command with all possible gadget chains. If the application responds with exceptions, which I found that to be the case, I think every time I've come across this kind of stuff, we can tell whether the payload worked. So if we get java.lang.runtime through an exception, java.io.io exception cannot run program, the target application has attempted to run that program. It doesn't exist on the target system. It's through an exception. Alternatively, if we get a class not found exception coming back, generally that's telling us that one of the classes used by our gadget chain doesn't exist on the server side. It's not present, it's not available to the application, it's not on the class path. So that entire gadget chain, we can disregard it. It's probably not going to get us anywhere. So with that, we've got entry point, we've got pop gadgets, we need some payload commands to execute. Ideally, we want to get from blind RCE to a shell, so we can interact with the machine and gain further access to the server or environment. So first thing that we might do is enumerate commands that are available. Again, we can use the same technique, cannot run program. If we try to execute whatever wget and we get that back, then we've not got wget as a potential command. There are some limitations with the YSO serial RCE gadgets because they use java.lang.runtime.exec with a single string parameter. So we can't have white space in command parameters. So the /a C users is fine. With this, we've got C:/documents and settings in double quotes, but the way that java.lang.runtime splits that command string up means that those the separate parts end up being separate parameters. So that won't actually work. There's also no shell operator support, so we can't pipe output from one command to another. We can't redirect output to a file or from a file. So, some common commands. Expect most people should be aware of these kind of commands. You might use in a Unix, Linux environment. Netcat shells, getting a payload from somewhere and executing it. It's also worth testing for the presence of interpreters, Perl, Python. They're going to, if we can get a script from somewhere, then those interpreters might be useful. Windows, we might do a copy command to a Windows file share to copy a shell, and we might also be able to use that to capture hashes. But even better than that, there's a command encoder online that will basically take arbitrary bash commands, PowerShell, Python, Perl, and encode it such that it doesn't use shell operators, and the parameters to the command don't contain spaces, so we can use whatever we want basically. So using base64 encoding, for example, that can be really powerful in attacking these with more complex commands. So that's everything that we need to execute a serialization attack. I'm going to look at some examples now. So first one, Spring Framework, specifically Spring Framework's HTTP remoting. This technology allows us to expose arbitrary Java classes over HTTP, so arbitrary Java objects, and it just does magic in the background. So a developer can basically just call a method on an object, and Spring will do some work in the background to send that over the network over HTTP. It's facilitated by a remote invocation class, which is part of the Spring framework. So like I say, when a client application calls a method on an object that uses Spring HTTP remoting, that client application behind the scenes, Spring Framework will generate a HTTP post request, send that to the server, decode that request, make the remote method call, and then send back a response. That's what it looks like. Java serialization. So Spring Framework serializes this remote invocation object, puts it in the body of a HTTP post request, sends it to the server, and that's an entry point for attack. So this script will attack that using the kitchen sink method. Generates all YSO serial payloads, puts the whole payload into the body of a HTTP post request, and then looks for the class not found exception, and it will tell us whether that pop gadget chain appears to be vulnerable or not, appears to be present or not. So if we run that script against an application using Spring HTTP remoting and it's vulnerable, then we'll get RCE. But this shouldn't happen. Applications that deserialize data should validate the type of the data being deserialized. So Spring Framework HTTP remoting expects me to send a remote invocation object to it. What I actually sent in this case was a hash set, which isn't compatible with a remote invocation. So when Spring Framework deserializes this hash set object, it then gets returned, and Spring Framework attempts to cast it to a remote invocation object, At that point, an exception is triggered, and exception response is sent back to the client, and nothing else happens on the server side. Now that happens, obviously, after the object's been deserialized, payload is executed, but it also happens before that payload ever reaches the application that uses Spring HTTP remoting. So if you're a developer using Spring remoting, you won't ever see that payload. But according to Pivotal, who makes Spring Framework, that's not an issue with Spring Framework. They refuse to fix it. One of their security team has a CVE for a similar vulnerability in JBoss. And I actually spoke to that member of their security team about this issue, and he said, it's not our problem, even though an application developer using this won't see the payload to do anything about it. So, whatever. Another example case study, Acme Money. Obviously it's not called Acme Money, but I can't talk about this one. Can't reveal the details of this one yet, because these are trying to fix it. So, that login packet from the start, obviously that's our entry point. The exploit was a bit more involved this time, but still easily done. So after I spotted that serialization data in the login packet, I didn't see the serialization header, ACED, so on. So I closed the application down completely, started at Wireshark to start a new packet capture, fired the application back up to see what was going on. And then following the TCP stream in Wireshark showed me this, which was everything that I needed to know. So first thing we've got here, serialization header, followed by 77, which is a block data element, 2, which is the length of the block, and then 0000, which is the data in that block. And we get this data coming back from the server, so 2 packets come back. First has a serialization header, second one has an object coming from the server. Next one that goes out to the server is a serialized object, 7.3. 7.2 is a class description. That's everything that I needed to attack the application. So this is the exploit script. We start off, we send the first packet that I just showed you, so ACED, so on. I did notice every time I did a packet capture of this, that packet was the same every single time, so that made it easier. I then receive 2 packets back from the server, 2 that I showed you. And I don't care what they are, I don't care about them, so I'll just chuck them away once I've received them. And then send a payload. So this is just a fire payload method that is part of that script that I showed earlier. So this method receives a serialized payload using one of the YSO serial gadget chains. The reason for the 4: in the square brackets is that in this case, we go back here, we've got the serialization header has already been sent to the server. That should only ever exist once in a serialization stream. And the payload generated by YSO serial that's passed to fire payload contains that serialization header. So the 4: just skips over that and it sends the rest of the payload in the second packet that we send to the server. So, as with Spring remoting, found that the underlying application didn't care if I sent it, for example, a Java hash set rather than java.lang.short, which is what it expected. You can see there in that bottom packet, the string java.lang.short. It didn't care that I sent it a different type of object. It still deserializes it and instantiates the object that I send it. So using the brute force script that I just showed you, I identified that we were using Commons Collections 3.2.1, which is well known to be vulnerable or to facilitate remote command execution through deserialization. So I did a quick test with a ping command and ended up with a few thousand pings hitting me because I forgot to set a limit. Yeah, so at this point, I've proved that I'm executing commands on the server, so I've won, essentially. But I thought this was quite an interesting example of what you can achieve with these kind of vulnerabilities. So I'm going to kind of carry on with the story, and obviously I wanted to get from executing commands to actually having an interactive shell on the box so I can do more, try and escalate my privileges. But this proved fiddly because I didn't have access to any of these commands. I did see that Perl was available, but honestly at the time I did this, I wasn't aware of the payload encoder that I showed earlier. So as far as I was aware with Perl, if I wanted to get, say if I wanted to do a reverse shell one-liner, I need to use the code use space socket, so I can't actually do that. So I ignored that for the time being. I eventually found that the TFTP command was available on the server. So there's a nice little library, Python library, TFTP, ran a TFTP server. That gave me access to the file system on the server. I was able to download files, upload files. So I uploaded a Perl reverse shell to the box. And it turns out that it was a AIX box, which honestly it's the only one that I've ever actually encountered. But I wanted more, so I only had a low privilege user shell there. Fortunately, most people don't prioritize operating system updates. So there was a nice local privilege escalation, except that it was written in C and the necessary build tools and libraries weren't available on the box. So I ended up rewriting the exploit in Perl, which was horrendous. But it was worth it because I got root on that box, and that allowed me to jump around the entire infrastructure. I was jumping between data centers, between pre-prod and prod. So raise your hand now if you think that you would know what to do if you saw that packet from the start. That's definitely an improvement. Awesome. So let's see if we can make it a bit more practical. So first thing that I've got is a Python script, which is essentially what the snippets were that I was showing, which automates some of the things that I've been talking about. So serial.py. The script can automate the process of delivering the various YSO serial RCE gadget chains to a target by either replaying a TCP conversation and injecting the payload at a location you specify, or by replaying a HTTP request. There's actually a Burp Suite plugin freely available that does this stuff for HTTP, so that might be a bit easier in those cases. But I regularly use the iterating through different payloads for TCP conversations. It also looks at the response data that comes back from the target, if there is any, and it looks for class not found exception and the IO exception that tells us whether payload gadget chains are useless or whether the commands didn't exist on the server. It's by no means a robust attack tool. It's just a dirty script that I've used a fair few times. And it can only handle simple protocols. So, for example, if there's a session sent back from the server and you need to use that session in subsequent requests, it can't handle that. But there is also serial brute, shortened.py, which basically has the same loop, which calls dispatch payload, and you just need to implement that to deliver a payload to your target application. So you can do things like get a session ID back and use that in the payload packet. Next thing I've got is serialization dumper. Again, it's on my GitHub, and we can use this to help work out where to inject a payload by passing it a sample serialization stream that's used by the application, target application, decoding it and working out where interesting elements are in that stream. And then lastly, Deserialization, however you want to pronounce that, which is basically a demo application to allow people to practice this. So run the server, run the client, and then pop some calculators. I'm going to attempt to do a demo. So there we've got the deserialization server. And this is the client. So, shut up. We run that, we can see some text appearing on the server. It's telling us that it's received data from the client, and I think it just asks us for a name. There's no reason for it, but asks for a name, and then a string to hash, so the server just hashes a string and sends it back. We can see the result printed out. So what we can do is run Wireshark, capture the packets, have a look at the data that's there, and see what's going on when that client-server interaction's going on, happening. And if this loads up, hey up, that's going to be horrendous. So let's just have a look, see if we can. So there, at the end of the data, we can see ACED0005. So we can see bits of data going back and forth. And we get down to here, we can see nb.dser.hash request. Looks like a serialized object. So I'm just going to get rid of that for now. Now what we can do with that data is we can take that whole conversation, or if we start from the start of it, we can take those packets, say, that are going outbound. That's one serialization stream, the inbound stream is another. If we take all the outbound packets, copy the bytes, and then pass them to serialization dumper, as long as we've got the start, we don't have to get the end. We can dump out as far as essentially looks like a serialization stream. So, quick example of that. Now we can see this is awful. Main thing that we're looking for here, we've got an object in the stream. That tells us that the server's going to deserialize that object at that point and gives us an idea where we can inject a payload. And then hopefully this will work. So here's what I made earlier, .txt. That contains the input for serial brute. Oh, bollocks, it's not worked. Whatever, right. You can all work out how to do that yourselves. It's on GitHub. I didn't sacrifice a goat. So, just to conclude, exploitation of serialization attacks is typically more involved than other common attacks, common vulnerabilities. It's important to understand what's going on, how serialization works, how the exploits work, in order to attack these vulnerabilities effectively. Same as SQL injection, we need to understand SQL to do manual SQLi. Exploitation is rewarding. Again, similar to SQLi, quite often get remote command execution. SQLi gives you the full database generally. You quite often see this stuff in big internal enterprise applications. That target that I've been talking about, that story I've been talking about, is something, I think it cost like 5 million to get a HTML5 interface for that application. It's ridiculous. So this kind of stuff isn't readily available to just anyone to research and pull apart. That's it. Questions? There's some references, some shameful plugs. I wrote an article which has a lot of the information that I've spoken about today. So go and check that out, have a look, give me some feedback. Tell me it's a load of rubbish if you want. Questions? Cool. Thanks.